Okay, today we are in section 1.4. This is question 8, which is kind of a difficult question. So in this question we have a mineral, some rock, and this rock has some uranium-238 in it. And it has a particular half-life. And this half-life is 4.51 times 10 to the ninth years. So just based on that information, we have the basic decay equation where the time rate change of the amount of uranium-238 is proportional to how much is there at any given time. Negative because it's decreasing. So at time 0, we have a certain amount of this in there. And so the solution to this differential equation is n of t equals n0 e to the minus kt. Now, while we do know the half-life, we don't know k. K is sort of the rate at which it is decreasing. So if we use the knowledge of the half-life, where we initially start with an amount n0, the half-life means we have lost half of the substance. So if I divide both sides by n0, I get this relationship. To get our hands on the exponent, we use the natural log. Natural log of 1/2 is minus kt, because the ln of e to something, and I get that thing back. If I use one of these properties of logs, the natural log of 1/2 is the same as the natural log of 1 minus the natural log of 2, but the natural log of 1 is 0. And so we can figure out what k is. What is that rate at which we are losing the uranium to radioactive decay? And so it is ln of 2 divided by t, and t is our half-life time. So I don't need to know this exact number right now, but we do know what k is. Now if you look at the wording, let's go back at the wording for the rest of this. So what's happening is initially the rock only has this uranium-238 in it, and it has no lead. So what happens is over time the uranium decays, and as it decays it makes a byproduct of lead. So over time the amount of uranium goes down, and as it decays the amount of uranium decays, but the lead goes up. And so now they tell me that the ratio of the amount of uranium right now to the amount of lead that's in the mineral body is 0.35. All right, so let's talk about that. So here at time 0, we have this rock has some amount of uranium-238 in it. All right, so we start off at time 0. We have an initial amount. So over time, it decays by our decay formula. We know what K is previously. And as it decays, we are going to produce lead as a byproduct. So if you look at this picture, we start off with a certain amount in 0. It's decaying. Over time, the amount of lead is increasing. And so we're looking at a time right now. So how much of the uranium-238 is there now? Well, it's by our decay rate, we have that formula. Now, how much lead is there now? Well, let's see. We started off with N0 amount. we've lost some uranium, and so the amount of lead that's in there is what we started with minus how much uranium is there now. So for example, if we started off with 10 grams of uranium and I've only got 7 grams now, that means there must be 3 grams of lead that formed. And so if I form this ratio of the amount now to the amount of lead, I know that that's 0.35. And so we put that ratio together. Looks rather complicated. So what I did was I factored out of the denominator an N0, and I also factored out an e to the minus kt. I did that because I'd like to get this thing to cancel. So let's make sure this is correct. If you multiply this back in, this e to the minus kt times e to the kt, that would be e to the 0 as the exponents add. So yes, this is correct. And so I get 1 over e to the kt minus 1 equals our 0.35. So I want to get my hands here on the time. Alright, so I start manipulating this item until I finally get down to bringing the 0.35 to the left, dividing by 0.35, and I know that's e to the kt. Alright, so if I take the natural log of both sides and then divide by k, I get the amount of time. The amount of time of when that ratio of 0.35 is true. And so I fill in what we previously found for k, flip this thing over, and then calculate this. Get a rather big number for time, but if you put it in scientific notation and keep it at 2 decimal places, you get 8.78 times 10 to the 9th years. Alright, another challenging problem is problem 10. So I have a tank, a spherical tank, got a radius of 5 feet, full of water, and it has a hole in the bottom, and the hole has a radius of 4 inches. So already, from all of your knowledge in physics problems, you see the units are not matching, so we're going to have to patch that up later. So they want us to use Torricelli's law for how long it takes the water to drain out of the tank. We're going to use the gravitational constant of 32 feet per second squared and not the normal units of 9.8 meters per second squared. Alright, so let's talk about Torricelli's law. Looks like the following. So got this a of y, time rate change of y, a small a, g, my gravitational constant. So what are all these things? So y of t represents the depth of the water in the tank at a particular time. So here's a depth of water right now, and as the water goes down because it's leaking, y of t is shrinking. So initially, when the tank is full, the height of the water is 10 feet. So as we go down in time because it's leaking, y of t is shrinking, and eventually the height of the water in the tank is 0. Alright, so got the water leaking out over time, going down towards 0. Now the A in our differential equation is the area of the round hole in the bottom of the tank. Well, it's a round hole, so the area is pi r squared, where this r is related to the radius of the hole. But the hole is 4 inches, so I need to convert this to feet, and so this is 1/3 feet, or the area is pi times 1/3 squared, or pi over 9. So the gravitational constant here is 32 feet per second squared, and the time is in seconds. That will become important at the very end. So A of y is the important part. It's the cross-section area of the tank at the water depth of y of t. So what do I see? Well, initially we're here, and the area at that depth is 0 because there's full of water. As we go down, we get a circle of a particular radius, and then it goes down more. The circle is getting smaller. It's going to reach a largest amount when the radius is 5 feet, and then the radius will shrink again. All right, so now if I look at this as a cross-sectional view, if the level of the water here is above the normal radius of 5 feet, here is r, and if it is under the normal radius of 5 feet, it's underneath. In either case, we get a right triangle. So here's the center, and if I go to an edge that's 5 feet, similarly here, center to edge 5 feet. The part in green is the important part, because I need this side for the Pythagorean theorem. Well, if we are at this height, this is y of t, here's the 5 feet, and so the amount in green would be y of t minus 5. Whereas here, 5 is the big one, and y of t is under, so the green would be 5 minus y. Now you might think, well, maybe that makes a difference with which height we're in, and it does right now. But if you look at the Pythagorean theorem and you work out both right triangles for r squared, so we go through that and you can look at that on both sides, what you notice is r squared is exactly the same. So it doesn't really matter if you are above the midline or under the midline in terms of r squared. All right, so here's my formula for the area. It's pi r squared, and here is my r squared. So if you look at this, this is a parabola. It is a flipped over parabola. And so initially, the area is 0. When we are at 5 feet, we're going to have maximum area. And when I get y is 10 feet, we get 0 again because it was full. So here, this is when it's empty. This is full. This is when we reach the midpoint of our spherical tank. All right, so if we put all this into my formula, all right, so here's my A of y, here's A. I fill in the gravitational constant. Square root of 64 is 8, and so we're there. Keep grinding away and simplifying. Now at this point, when you get your y's together for separating the differential equation, I've got y to the 1 over y to the 1/2. So y to the 1/2, this is y squared over y to the 1/2. So when you subtract the exponents, you get y to the 3/2. All right, and so as we're working away here, the pi's went away because you canceled on both sides. So integrate this, and we are still calculating. We get down to the final relationship. And so at t equals 0, the tank is full. So if the tank is full, y at that point is 0, t is 0. And so we get this relationship for C. All right, so when the tank is empty, y is 0. So if y is 0, this will be 0, this will be 0. I can solve for t, and we just found this relationship for the constant C. All right, so we get this nice ugly formula with some algebra. And if you isolate the t, it's going to become positive when I go to the left. Multiply by 9/8 to clear the fraction. We get our formula for t. And so I took out a 10 to the 3/2 because I didn't really want to grind through this. All right, and we were able to simplify some of this and make it look nicer. So the time is 3 times 10 to the 3/2. And so if you calculate this, you get 94.868 seconds. Because remember, our gravitational constant was in terms of seconds. But they wanted to know how much time in minutes. So you have to take this answer we got and divide that by 60.